Dear participants, welcome to the day 2 of FDP sessions. Now it is my honor and privilege to welcome Dr. Asadi Srinivasulu sir for FDP's day 2 session on quantum circuits and gate models. Dr. Asadi is an accomplished academician with over 24 Dear participants, welcome to day 2 of the FDP session. Now it is my honor and privilege to welcome Dr. Asadi Srinivasulu sir for FDP day 2 session of quantum circuits and gate models. Dr. Asadi is an accomplished academician with over 24 years of teaching and industrial experience. He holds a PhD in data science from JNTUA, Anantapur, India. He is currently pursuing a double PhD in artificial intelligence at IIIT Allahabad. Dr. Asadi has completed his MTech in Intelligent Systems from IIIT Allahabad and BTech in Computer Science and Engineering from Sri Venkateswara University, Tirupati. He is currently a visiting professor at CRC Care, the University of Newcastle, Australia, and served as a subject matter expert at Deloitte, Delhi from 22 to 2023. Previously, he has served as a head of research and open labs in information technology at Blue Crest University, Liberia, and held the position of head of Department of Information Technology at SV College of Engineering, Tirupati from 2007 to 2009. Dr. Asadi research interests lie in data science, big data analytics, artificial intelligence, machine learning, cloud computing, robotic process automation, and software engineering. He has authored 9 textbooks. He has published over 198 research papers. He has also filed 4 patents in the field of AI and data science. As a mentor and academic guide, Dr. Asadi has successfully supervised 3 PhD students and guided many MTech and BTech students. He has ejected 50 PhD theses across 19 universities, which shows his strong evaluation skills and research expertise. He is a recognized leader in his field. Dr. Asadi holds several prestigious certifications, including IBM, Microsoft certifications, and from other platforms also. He is an active member of various professional bodies, including IEEE, ACM, and CSI, and also he is serving on the editorial boards for numerous journals. He is also a reviewer for several publishers, including Springer, IEEE, Elsevier, and InterScience. Dr. Asadi has received multiple accolades for his contribution, including Bharat Vidya Ratna National Award in 2018, Lifetime Achievement Excellency Award in 2022, and Best IT Researcher of the Year from ITAP 2020. His international engagements include visit to countries like Malaysia, Singapore, Ghana, Kenya, Dubai, Sri Lanka, and Australia, where he has participated in and also contributed to academic conferences, seminars, and research collaborations. Dr. Asadi has also conducted over 127 national and international workshops, conferences, and seminars as a resource person. Further, his position as a thought leader in his domain. His significant contribution to AI and data science have earned him recognition in both academic and industrial circle, making him a respected figure in the global research community. Participants, we are We are familiarized with the circuit representation of quantum algorithms. We will be familiarized with the circuit representation of quantum circuits and gate models. So I request Dr. Asadi sir to kindly deliver the session on quantum circuits and gate models. Over to you, Dr. Asadi sir.
Thank you, madam, for a nice introduction. Can I share my screen? Please allow me to share my screen.
Sure, sir.
Yeah. Still, host not allowing sharing my screen, madam. Yeah, now it is okay.
Sir, now it's available, sir, at your end. Please check
Yeah.
once.
I'm
Okay.
sharing my screen, madam.
Okay, sir. Thank you, sir. Thank you.
Thank you. 1 second. Yeah, my screen is visible, ma'am. Yeah, thank you for a nice introduction. Today, a warm welcome to a second day Atal online 6 days faculty development program on quantum circuits and gate models. Actually, the organizers given that topic under my big topic like quantum computing for cyber security, next generation applications with artificial intelligence, machine learning and deep learning techniques. Under this topic, I'm going to demonstrate quantum circuits and gate models, how it is a building block for solving quantum computing applications by using quantum mechanics with the help of superposition and entanglement concepts. Let me justify the title of the today's concept, quantum circuits and gate modeling under this quantum computing. Quantum, what is the meaning? Yesterday you might have attended, what is the meaning of quantum? Pocket of energy. That means, now, unlike traditional binary system measurement like 0 or 1, but we are measuring in qubits. Quantum is a pocket of energy, is nothing but quantum. Computing is nothing but processing, calculation. Computing started in the way back, IBM started. And it starts with a single processor, multi-core processor, parallel processor means parallel computing, then green computing, then grid computing, then cloud computing. Now the buzzword in the industry is called quantum computing. Is a new paradigm model which solves quantum computing operations with help of superpositions and entanglement, major building blocks of this quantum computing applications, especially in computer science applications like in drug design, cyber security, and healthcare analytics, education analysis, and cyber security domain, and financial computing, financial management. Everywhere we are using this quantum computing by using various buzzwords, latest technologies such as artificial intelligence technologies, statistical models, AI models, machine learning models, and deep learning models we are using to solve complex applications by using quantum computing. Okay, this is my background, madam already explained. So my major specialization is artificial intelligence, one PhD in data science and another PhD from artificial intelligence. And these are my research areas. Right now I am solving complex applications under artificial intelligence, machine and deep learning, data science, cyber security, health data analytics. Right now at University of Newcastle. I'm solving groundwater data analytics, soil data analytics, PFAS data analytics. These are the various publications you can see in IEEE Explorer, RCID, Scopus, Science Citation Index, Web of Science. So many publications available. Uh, Nearly 40 in SCI and 40 more than Scopus journals are available. I'm a corporate trainer on data science applications. It is the data science is the process of extracting meaningful interested patterns by applying AI, ML and DL techniques. And the same generative AI is nothing but creating new applications which is not available in the database by using machine and deep learning techniques. We are solving various applications, audio, video, text, graphics, etc. So this is the syllabus of generative AI, 13 core subjects and 4 case studies. Then I'm a corporate trainer on cyber security applications using machine and deep learning techniques. So this is the syllabus of cyber security. Today I'm going to demonstrate 5 case studies in cyber security by using quantum computing with the help of quantum circuits and gate models. How it is playing a vital role. It is a building block for a quantum computing concept. So these are the 13 concepts and followed by the real-time applications. And this is the syllabus of data science and 4 case studies. So within 60 seconds, what is happening? How many users are connected to this internet world? I would like to see the statistics of internet. What is internet? Internet is a network of networks. Network is a interconnection between the computers in the fashion of local area network, wide area network, metropolitan area network. How many users are connected in this 60 seconds? I would like to see the statistics. Internet is developed by Bold, Bernanke, Newman. 3 scientists has been proposed this internet. So we are using a cloud computing in the backbone for storing huge volume of data in the data center. So that's why cloud computing is an internet-based technology. The backbone for cloud computing is a data center and virtualization. Virtualization is the ability to perform multiple tasks in a single system. By using VMware technology hypervisor, we can install at a time 2 operating systems like Windows and Linux operating systems. There are popular virtualization technologies like VMware hypervisor, Zen Virtual Iron. In cloud computing, one more backbone is a data center. Data center is a combination of high computing servers at one place is called a data center. Each company having their own data centers, which is located at different locations. So within 60 seconds, how many users are connected? 6,94,000 videos hours viewed within the 60 seconds. 18.8 M text message sent, 2.4 million Google searches happened, 11,035 fake accounts removed. Why I am explaining all these? Because we are extracting data from various sources. So wherever data is there, there is a security problem. In order to protect our data from the system, server and data center, we are using there are the security mechanisms like cloud computing security and quantum computing security. If you use quantum security, quantum computing security, so nobody unbreakable end users, nobody can break such type of encryption mechanisms we can do with help of quantum computing. Keep in mind, if you click this URL, you are going to see the statistics of number of users are connected in this world. See, I have clicked this URL. Now I am retrieving the data from various sources of worldwide. Current world population. Can you imagine? See here. So 8,245,522,000. See, Today births itself 2,82,700 something. This year, can you imagine? Deaths today, deaths in this year. So where I am getting this huge volume of statistics from various sources. Very interesting. See here, the number of populations growth today. If you see the statistics of top 10 countries, India is the number one, China, USA, Indonesia, Pakistan, Nigeria, Brazil, Bangladesh, Russia, Ethiopia. See, we are getting huge volume of data from various sources. Where we are going to store this huge volume of data, how many systems and servers and data centers are required to store huge volume of data. That's why we are going to use cloud computing concept, data center and virtualization. Okay, so this is for your reference. Just I would like to show the statistics of huge volume of data, because I am going to use a huge volume of data for to perform the complex applications by using quantum computing. Today I am going to demonstrate 5 applications. So www invented by Tim Berners-Lee, World Wide Web. It shows the internet live statistics.com, how many internet users connected within 60 seconds. Can you imagine? See here, total number of websites opened by using this website, email sent today, Google searches today. So same thing I have incorporated in this slide. Number of users are increasing. That means automatically the size of the data center also increases. This is for your kind information. Just I am showing where we are getting huge volume of data. If you press capital A in the system, system cannot understand capital A. Internally, it converts into ASCII format. ASCII stands for American Standard Code for Information Interchange. Okay, so computer understands only binary language. This is a traditional systems, like 1 bit is equal to 0 or 1, 4 bits is equal to 1 nibble, 8 bits is equal to 1 nibble, 8 bits is equal to 1 byte, 4 bytes is equal to 1 word, 4 words is equal to 1024 bytes. Likewise, we are measuring 1024 bytes equal to kilobytes, megabytes, gigabytes, terabytes, petabytes, hexabytes, octabytes, zettabytes. Hi, I am Robo. My speed is 1 terabytes. My memory is 1 zettabyte. Thanks to director Shankar and Rajnikant sir, they have introduced that terminology in that Robo movie. Earlier, also available, but we don't know this is the terminology we are using. 1024 zettabyte is equal to 1 yottabyte. 1024 yottabyte is equal to 1 brontobyte. Yesterday night again I searched in the, is there any terminology is presented? Yes, there are 2 more terminologies presented. 1024 yottabyte is equal to 1 brontobyte. 1024 brontobyte is equal to 1 geobyte. After that, if you ask me, it says that infinity. Same thing we are incorporating in the normal range and big data range. In mathematical representation, kilobyte is 10 power 3, megabyte is 10 power 6, gigabyte is 10 power 9, terabyte is 10 power 12, and petabyte is 10 power 15, hexabyte is 10 power 18, zettabyte is 10 power 21, yottabyte is 10 power 24, brontobyte is 10 power 27, geobyte is 10 power 30. This is the way we are measuring data in quantum computing also. So this is the data science training syllabus. This is the syllabus of 13 subjects. I'm skipping this syllabus, and traditional systems, servers and data center uses binary number system. Keep in mind, classical representation, computer understands only binary language called 0 or 1s. So these are the projects I have executed and implemented with the help of my masters and PhD students. So far we have completed 153 projects under my artificial intelligence laboratory. Recently we have done AI for smart policing, AI, blockchain, IoT, big data and 5G in a seaport security management, prediction and detection of soil properties using machine and deep learning techniques. Okay, so there is a interesting question, my dear participants. Nearly 120 participants are there. So one more quantum computing application I would like to explain and demonstrate. A very interesting question. If I am asking when is your date of birth, immediately you are saying, sir, my date of birth is 15th July 1978. Okay. So if I am asking the question, when is your death date? Immediately you are getting angry. Sir, what is this stupid question you are asking? When is my death date? Yes. By listening this question, you are feeling irritation and you don't want to listen such type of question. So, but for this question in this era, in this digital domain, in this terabytes of quantum computing era, we are solving the problem like death date by using life to vector model. The model is nothing but simplified version of the reality, and it uses natural language processing with leveraging of deep learning and machine learning techniques to generate a vector representation that captures rich information about various aspects of input data we are taking as a human life. This model takes parameters like biological data, what is lifestyle of factors, environmental influences to predict the actual lifespan and death date. So this is the input for a system: biological data, name, date of birth, height, weight, lifestyle, factors, genes, and what sort of exercises you are doing, what sort of diet you are taking, and finally I'm finding the number of years as a lifespan. This is very interesting question. Under quantum computing, I'm demonstrating this application. Write a Python program to find the death date by using human input human input data like biological data, lifestyle habits, and genetic traits using a rule-based scoring method, and by leveraging machine and deep learning techniques. So here I'm importing NumPy by using Python programming. I'm going to demonstrate this application, very interesting application. Now see here, I'm going to demonstrate this application. So if you don't know Python also, very simple. Okay. It takes only 2 minutes uh, to install a Windows version of Python. So if you once from Google, if you install successfully, you can type Python. It shows the version of Python you are using 3.13.7. Okay, there are two ways of executing Python. One is IDLE and one more is a scripting way. So I don't want IDLE like this is called IDLE. I am executing simple program addition of two numbers a plus b. I'm performing. So this is IDLE. I don't want IDLE. I want to execute in scripting way. I want to write my own program. That's why I'm shifting to scripting way. So this is the way I can swap into scripting way. Notepad space. My file name is so I'm writing my own program. Write a Python program to find the death date by using machine and deep learning and life to vector model. See here, this is my aim of the program, and I have successfully installed Python, and I'm importing NumPy, Matplotlib for visualization, defining function, and predict lifespan based input factors, adjust a score based on biological data like height, weight, gender, etc. And we are adjusting score based lifestyle and adjust the score based on genetics, and we are clamp score to realistic lifespan. Then sample input data I'm taking like biodata, name, gender, blood pressure, cholesterol, BMI, body mass index, lifestyle, exercises, diet, smoking, drinking, etc. And finally, we are predicting the lifespan and the death date of a human being, a person, by using plot the bar chart in the labels like average lifespan and predicted lifespan. So I'm going to demonstrate this application. Python space. See here. So I have given my own biodata of myself, and I have see my predicted lifespan is a 77 years. See here, my output is visible. Please acknowledge me. And x-axis I'm having average lifespan and predicted lifespan. So my predicted lifespan is 77 years by using my own biological input data. This is a quantum computing application. Keep in mind, very interesting application, my dear participants. Now I am going to demonstrate. Okay, so I'm closing this one. So these are very interesting application I'm showing. So same thing I have incorporated. See here, then same program, input data, predict lifespan. See here, 95 years. Depends on the input constraints. If you are increasing, automatically your lifespan will be increases. So same thing I have incorporated in this slide, and lifespan one more program you can see here. One more program I am going to demonstrate. CLS, clear the screen, notepad space, lifespan. See here, very interesting problem. Write a Python program, same thing. So this is also lifespan. So if I am giving a input of a human being, like actual lifespan and predicted lifespan, like depends on the input constraint, 64 years. Okay, so I'll stop here this one. Now I'm moving to my concept, quantum circuits and logic gates. Today I'm going to demonstrate. Very interesting. I have a YouTube channel. If you type my name, Dr. Asadi, you will find nearly 500 videos available across the world. Every day I am demonstrating various technologies like generative AI applications, data science, cyber security, cloud computing, quantum computing, big data analytics. Okay, so there are various technologies are available. If you type my name, Dr. Asadi, and subscribe my channel and forward to your friends. Okay, so welcome to today's session. Okay, one second, one second. So this is today's concept I would like to demonstrate. My concept is quantum circuits and gate models. Yesterday, you might have uh, grabbed all the knowledge of quantum computing, how it emerged as a computing concept from the quantum mechanics with the concepts of building blocks like superposition and entanglement. So these are the top 10 concepts I would like to explain. My introduction to quantum computing and qubits. Today's concept is quantum circuits and gate models, and how this quantum computing is useful in quantum cryptography and post-quantum security protocols, and the quantum machine learning fundamentals, how AI and machine and deep learning techniques going to help classify the cyber security threats, classification, clustering, association rule mining, outlier detection by using statistical AI and machine and deep learning models, quantum enhanced threat detection and anomaly prediction by using machine and deep learning techniques, hands-on programming by using Python programming from IBM QSkit and IBM Quantum Lab for cyber use cases, quantum algorithms for secure key distribution and encryption, AI-driven quantum network intrusion detection system, quantum deep learning models for malware classification, clustering, association rule mining, outlier detection, hybrid classical quantum architecture for cyber security, and future trends like quantum AI for cyber defense in cloud and edge environments. So this is the agenda for the major concept. Under that, I am taking today's concept, quantum circuits and gate models. Okay. So now, so everybody knows what is meant by quantum computing. What is meant by quantum? Quantum is nothing but a qubit measurementation. Pocket of energy is called quantum, according to Pauli. Okay. According to the scientist, he has given quantum computing is a new computing paradigm. It's a model, simplified version of the reality. The computing means processing, single computing processing, multi-core processing, parallel computing, and cloud computing, grid computing, quantum computing. Means the computing power is quadruple. You can't imagine such a huge combinations with the help of superposition and entanglement we are generating. So that uses qubits is nothing but quantum bit, not like traditional systems like binary number system, ones and zeros. Instead of classical bits, we are using qubits. Is the basic unit of quantum information. Why we are using quantum computing? In order to solve complex problems very fast and very fast encryption, especially in cryptography. If you are a sender to destination, you are giving as a plain text by applying quantum computing cryptography method and it converted into cipher text. You cannot unbreakable cryptography we are performing by using quantum computing, and we are solving optimization and large scale simulations by using quantum computing. By using quantum computing, there are many giants like IBM, Google, and Microsoft. They have developed their own quantum computing models. And why we are need quantum computers in key application domains like drug discovery, material science, financial modeling, cryptography, especially, we are converting from plain text to cipher text by using quantum computing. Number of operations by using superposition and entanglement, we are performing so many operations in order to hide the data, in order to drug discovery, material science, financial modeling, cryptography, and medical diagnostics and artificial intelligence, etc. See, traditional systems, computer understands only binary language, either 0 or 1. That is a classical computing. Whereas in qubit quantum computing, 0 to 1 means 0, 0.1, 0.2, and so on, 0.9. That means 0, both combination 0 and 1 simultaneously we are performing numerous computations by using quantum computing with building blocks like superposition and entanglement operations. There are various algorithms I am going to demonstrate today under quantum computing. So what is the major difference between classical and quantum computing? Traditional systems uses binary language, that is zeros or ones, and quantum computing uses 0, 1, and both at a time simultaneously can exist in a superposition of both states simultaneously. We are computing numerous operations. So that's why you need to have the basic difference between classical computing versus quantum computing. See, binary system. Binary means 0 or 1. Capital A value is 65. If you divide it by 2, we are getting binary equivalent number is 100001. Okay, so computers understands only binary language. So, whereas in quantum computing, the measurement of quantum computing in terms of qubits, quantum bits, 0, 1, both simultaneously with the combination of operations, numerous operations. In classical computing, we are using transistors and logic gates, whereas in quantum computing, we are using superposition. Means the combination of 0, 1 and both simultaneously we are getting 0 plus 1 and we are getting superposition. 0 plus 1 by square root of 2. That is a one superposition number. So whereas in classical computing we are using memory storage, we are storing permanently and temporarily. Whereas in quantum computing we are using quantum tunneling. See, a huge volume of computer servers in leakage, tunnel off. Okay, so processing methods we are using in classical computing, whereas in quantum entanglement is nothing but one or more combines and making a link, association between more than two particles and making a link, that is called quantum entanglement, so that we are performing various operations. That's why in this binary logic and a transistor with the quantum systems, we are integrating with the qubits, superposition, tunneling, and entanglement. So how quantum computing works? Yesterday you might have seen qubits is nothing but quantum bits. 0 to 1 means 0 0.1, 0 0.2 and 0 0.9 and so on, so many combinations. And it becomes as a superposition. See, in sine wave, so 0 plus 1 by square root of 2, we are getting a superposition number of operations. Entanglement is nothing but one or more, making a link and association between 0 to 1, 1 to 0, many association links we are generating in order to perform various combinations. We have quantum gates or building blocks of quantum computing. Here Adiabatic gate uses a single qubit computations we are performing by getting superposition and measurements like 0 to 1, 0 to 0 0.1, 0 0.91. We are solving this quantum computing in terms of qubit, superposition, entanglement, gates and measurements. These are the jargon of quantum computing. Keep in mind. So here we are using Adiabatic gate. It puts qubit in superposition. We are giving a single qubit operation and we are getting superposition with combination of 0, 1 and both simultaneously. And C naught, it copies phase to create entanglement. Okay, so we have a flip gate and we are getting superposition of Adiabatic gate and entangle with combination of Adiabatic gate and C naught gate. We are performing operations. And what is the architecture of quantum computing workflow? Yesterday you might have seen there are various layers. You can see application layer. Okay. And we have a classical processing, digital processing, analog processing, and quantum processing. See here, all of you, application layer, we can see the number of algorithms and results. In classical processing, we are using micro instructions and calibrations and tuning and measurements. Whereas in digital processing consists of digital control signals, digital readout signals, etc. In analog processing, we are using analog control signals, analog readout signals, etc. In quantum processing, we are using superposition like quantum processing unit, qubits and quantum bits and superposition, entanglement and various quantum computing. These are the architecture is a structure of various physical and software components and connections among them by using various layers. So this is the classical computing versus quantum computing in various parameters like computing units. We are using 0 or 1 in classical computing, whereas in quantum computing we are using qubits which can represent both 0 and 1 simultaneously. Computing capacity means processing huge volume of computing, like capability increased linearly 1:1 with the number of transistors, whereas in quantum computing capability increased exponentially with the number of qubits with the help of entanglement and superposition. And error rates and environment, it is a parameter in classical computing. Low error rates and can operate at room temperature, whereas in quantum computing high error rate, some quantum systems need to be kept so ultra cold, then only it can work multiple operations at a time. And suitability of classical computing for routing, processing, etc. Whereas quantum computing, it is suitable for complex applications like drug discovery, financial computing, etc. So that's why the major difference between in computing units, capacity, error rates, and suitability for processing tasks. See, whereas quantum computing fundamentals what are the applications, and what are the tools in a user-friendly environment. See, fundamental operations and assistance we can see in quantum computing. We are solving complex problems, high speed processing, post quantum cryptography, confidential data processing, etc. So we are solving innovative commercial applications like design robotics applications. We are using quantum computing because as a humanoid robot, we are performing multiple tasks. As a human, how different perceptions and different thinking, rational thinking, climate prediction, financial modeling, smart transportation, telecom. So there we are using this quantum computing. Roots and pillars like basic building blocks for this quantum computing is superposition and entanglement and decoherence. Decoherence is nothing but unlike like binary system. Okay, so there are various applications of quantum computing like data security. For unbreakable security, we can use quantum computing because plain text we are converting into ciphertext by using quantum computing algorithms, and boosting AI, urban traffic flow modeling, improve climate prediction accuracy, designing and cutting edge medicines. We are using quantum computing applications. So where IBM, they have started their own quantum computing model called Qiskit, and Microsoft Q Sharp Hash, and Google started their own quantum computing Circ, and Rigetti Computing, they have started PyQuil, and ETH Zurich, they have their own quantum computing Silk, and Quantanium, they have their own quantum computing TKET computing models. So by using this quantum computing, we are solving future problems like in financial computing, drug discovery, and various medical applications. We are using quantum computing. So why this quantum computing plays vital role in computer science irrespective of the domain? It came from the quantum mechanics, and especially drug design and molecular simulation, very fast drug discovery simulations we can perform by using quantum computing, and medical diagnostic, and various radiotherapy, cancer disease prediction detection applications. We are using AI in healthcare enhanced by quantum computing, genomics and personalized medicine applications. We are using this quantum computing. This is the quantum classical computing integration framework, which integrates n number of processing layers like quantum hardware. We are measuring with qubits, combination of 0, 1 and both simultaneously is called qubits. It's nothing but quantum bits. Quantum connectors, interconnect circuits for control operations, and QRAM. So this comes under quantum hardware. Quantum processing unit, we are using quantum registers, quantum logic gates, quantum memory. Whereas, so the difference between quantum and classical computing interface, we are solving business applications in high level range. We are using quantum processing environment like quantum assembly language, quantum algorithms, quantum circuits from cloud data center. Cloud data center is a combination of high computing servers at one place at remote location. I am accessing 24/7 with the help of cloud computing concept. That's why without internet you cannot access any kind of service based application with help of cloud computing. It is a major drawback. Okay, so still that problem is R&D is ongoing. Google already started. What are the advantages of quantum computing? See, there are plenty of advantages like explore multiple possibilities. Okay, number of operations we are performing parallelly. Single computing processor is different than multiple computing processor. So multiple computing processor is nothing but parallel processing computing. Then it goes to the cloud computing, then goes to the green computing, then quantum computing in terms of qubits. We are solving unprecedented computational speed. and we are tackling intractable problems, revolutionizing AI and machine learning problems. There are various advantages like unbreakable encryption we are solving with help of quantum computing, and integration of entanglement and personalized medicine, breaking current encryption methods, breaking the language barriers, and accelerating climate change modeling, optimization logistics, enhanced material design and discovery. There are plenty of advantages we are getting with help of quantum computing. I am going to demonstrate now 5 applications by using quantum computing across industries. They are showcasing especially the impact of quantum computing. Recently, Nara Chandrababu Naidu introducing quantum computing center at Vijayawada. So it can perform all educational issues, medical issues, financial computing, logistics, chain management, material science, healthcare, and artificial intelligence problems where we can solve within fraction of seconds with the help of quantum computing. And not only those in artificial intelligence, science and engineering, and to solve complex based applications by using quantum computing. In cybersecurity, unbreakable cryptography, we are solving the problems. Quantum cryptography, weather forecasting, financial modeling, drug discovery, whatnot. Wherever data is presented, there we are using quantum computing in order to solve complex applications. That's why still R&D is ongoing in quantum computing. There are, if you are interested to do any research, masters and PhD, try to solve these are the problems still available. Quantum supremacy and quantum error correction, quantum ethics and security, quantum and decoherence, and qubit scalability, quantum software development, noise and interference, quantum communication, quantum hardware reliability. These are the few challenges are available in order to solve research problems. So few more problems like algorithm development you can use as a concept in quantum computing. Hardware development, quantum decoherence is nothing but normal classical binary system concept. What are the challenges? Very slow. If you are using our traditional systems uses binary system, if you use a quantum computing within fraction of seconds we are solving very complex applications. So error correction is one of the challenge in quantum computing. Scalability is a problem, and trained telnet standards and protocols, classical computer interfaces and hardware development. Still there is a chance research gaps and issues. You can choose this one as a challenge, and you can perform your research in this domain. The first application I am going to demonstrate, write a Python program as a beginner. First, what is meant by quantum computing concepts while combining theory, text explanation with the practice. I am going to demonstrate quantum computing using what are the latest applications under quantum computing. I am going to show you demonstration of quantum computing applications. It uses pandas and matplotlib. I have taken a data set for a description of pandas package. For visualization purpose, I am using matplotlib. Now I am going to demonstrate first application, quantum 1. So see here, I am clearing the screen, notepad space. So this is the first application, write a Python program to perform combines theory with the practice, data visualization to help beginners. I am a beginner, sir. I don't know much knowledge about quantum computing, how to analyze related data. So for that one, I am using two libraries like pandas and matplotlib. For data set description, I am using pandas. For data visualization, in order to generate a pie chart, bar chart, and a heat map, line chart, area map, I am using a matplotlib. and just I'm printing this introduction to quantum computing and qubits, and I'm using various text as a input for my data set, and create a sample data for visualization. I'm reading as a data frame, and PD means pandas library, PD.data frame. I'm using a bar chart. I'm demonstrating which applications are closely associated with quantum computing. See here, I'm going to demonstrate Python space. Sir, I'm a beginner. I don't know much about quantum computing. So, which applications are more closely related to quantum computing? Quantum computing is a new paradigm, means is a model, a simplified version of the reality in order to solve complex applications of computing paradigm that uses qubits instead of classical bits. So in order to solve complex problems very fast, such as in cryptography, first application of quantum computing, cryptography and optimization and large scale simulation and medical diagnostics and etc. So these are the applications are very close to quantum computing concepts in quantum mechanics to solve computing applications with help of building blocks like superposition and entanglement. So this is the first application, and now I am moving to next concept is quantum circuits. What is meant by quantum circuits? Quantum circuits like computational models. Model is a simplified version of the reality where qubits is nothing but quantum bits are manipulated using quantum gates, and similar to how classical circuits use logic gates like AND gate, OR gate, NAND gate, NOT gate, etc. So the fundamental framework for executing quantum algorithms, it uses various operations like superposition, entanglement, and interference. So that's why quantum circuits are designed and simulated in programming frameworks like IBM. IBM having their own quantum computing model programming called KeySkit, and Google having Skirk, and Microsoft having QHash. These are the simulated programming frameworks. If you are having data or any input, you can use this framework to solve complex applications. Examples of this quantum circuits we are using Hadamard gate. It creates superposition. The C naught gate controlled NOT gate and entangles two qubits, and this quantum circuits implementing Shor's algorithm for factoring, especially for Grover's algorithm. For such purpose we are using Grover's algorithm on these gate models. So gate models and you can quantum gates are building blocks for this quantum computing quantum circuits. So quantum circuits and gate models. See, quantum circuits consists of qubit state preparation, qubit, and result measurements, and quantum gate model we are getting. That means it can solve a step-by-step process where the qubits combination of 0, 1 and both simultaneously and prepared, transformed using quantum gates, and finally measured to extract computational results. So there are three types of quantum circuits and gate models. Today I am going to demonstrate single qubit gates. So the best example for a single qubit gates is a Hadamard gate. So this is manipulate its state on the Bloch sphere, like create superposition from basis states. Example of single qubit like 0, and it becomes 0 plus 1 by square root of 2, that gives superposition. So Pauli gates like XYZ analogous to NOT and rotation operations, example X0 operation we are getting 1. So Pauli gates in you can have a single qubit gate only, this one Pauli gate and Hadamard gate. Then a single qubit gates like see here we are getting combination superposition like 0 plus 1 by square root of 2. That is called superposition, like 0 0.1, 0 0.2 and so on 0.9. That means we are getting a superposition number of operations. And so I am executing this program, write a Python program to simulate and action of Hadamard gate and Pauli X gates on zero state, calculate the resulting probabilities and visualize them with a bar chart while saving this data for data analysis. See now, so I am going to demonstrate this Hadamard gate. I'm clearing the screen. So next program, notepad space, see here, notepad space, quantum. Okay, so write a Python program to simulate the action of a Hadamard gate and Pauli X gates on zero state, calibrate the resulting probabilities and visualize them with bar chart while saving. See, I am going to demonstrate bar chart. For that one, I am importing a NumPy for data set description. So I am representing in matrix representation, import for matplotlib for visualization purpose, and pandas for data set description. So basic states I'm using 0 and 1 with help of NumPy, numeric calculations. So NumPy, the short form is np.array 1001. So this is a D-type complex data I'm taking. Single qubit Hadamard gate and Pauli gate I'm using. So 1 by np dot square root of t multiplied by np dot array with the combination of Hadamard gate and with np dot array of 0, 1, 1, 0, that is Pauli X naught gate. Then apply gates, we are performing probabilities in a computational basis we are getting. So this is a representation called probability, means 0 to 1, both combination 0 0.1, 2 and so on 0 0.9. Then make a table and save. We are making the table here. Then we are taking a CSV, comma separated variable data. Then we are plotting a matplotlib, single figure and custom colors we are using. Then we are developing a figure. That figure shows the width and bar chart I am developing. And finally I am showing this x-axis, y-axis with a title called single qubit gates, that is Hadamard and Pauli gates. I am demonstrating it is with a bar chart. Now see here, Python space quantum. Okay, so see here, I am demonstrating a Hadamard gate. My screen is visible. Please acknowledge me.
Yes, sir.
My screen is visible.
Yes, sir, visible.
Yeah, thank you so much, ma'am. So here, so single qubit gates we are implemented with help of Python programming with the building blocks of superposition and entanglement by using Hadamard gate, single qubit and Pauli gate. We are using this one. See now, we are getting, this is called a single qubit gates plot. So now I am moving to next next application, multi-qubit gates. So in this multi-qubit gates, we are having CNOT, swap gate and Toffoli gate. And advanced gate is nothing but a Bell state generator. These are the 4 models you need to implement. You need to know how many operations we are performing. It is 2 or more qubits, quantum bits, and are essential for entanglement. 2 or more making a link, association, bond, and entanglement and conditional operations we are performing. C naught is nothing but a controlled knot. That means it flips the target qubit of the control qubit. 1 becomes 0, 0 becomes 1. Example, see here, 1, 0. So 0 means controlled bit, 1 means target bit. We are getting 1, 1. Swap gate is nothing but exchange the states of 2 qubits. Okay, 0 becomes 1 and 1 becomes 0. That is called a swap gate. Toffoli gate is nothing but, so complementary controlled NOT gate. It is a multi-qubit gate. It is a 3-bit So 3 by 3 matrix representation we are showing for 3 qubit gate that flips the third qubit if the first two are both 1. See here example basis 110, that is probability we are getting the operation 111. So the first bit is a target bit, remaining 10 controlled bits, it becomes 0 becomes 1 in Toffoli gate. Then Bell state generator, it is a multi-qubit gates. The combination of a Hadamard gate and a controlled NOT gate, it produces the entanglement states like, so 0 combination plus 1 combination divided by square root of 2. Such kind of gate is called Bell state generator. You might have studied digital computing. Okay, digital logic and switching theory. There we have seen AND gate, NOT gate, OR gate, XOR gate, etc. Universal gates. So same way we have a multi-qubit gates in order to perform multiple operations. See multiple qubits gates we are having. C naught, see we are having. So Q1 becomes Q1 target class and Q2 Q1 XOR Q2. So Bell state combination of Hadamard gate and C naught gate, it becomes 0 and with combination 1 divided by square root of 2. So 2 qubit swap 0 becomes 1, 1 becomes 0. Here Q1 becomes Q2, Q2 becomes Q1. So Toffoli gate with the help of 3 qubit. So that is Toffoli showing how they operate on 2 or more qubits to perform essential quantum operations like entanglement, swapping and controlled logic so that we are increasing parallel processing computing. We are getting result within fraction of seconds by applying these multiple qubit gates. So for that one I am developing one program, write a Python program to perform multi-qubit quantum gates by using CNOT, swap, Toffoli gate and Bell state generator and calculate their output probabilities and visualize the before and after results with the help of bar chart. I am going to demonstrate a third application. So notepad space quantum. So this is a write a Python program. See here, my dear friends, write a Python program to simulate multi-qubit quantum gates, CNOT, swap, Toffoli and Bell state generator. We are calculating their output probabilities and visualize the before and after results with bar chart. See, we are having operations like import, NumPy, Matplotlib, Pandas. Utilities we are using. See here, utilities we are defining a function and a operation, for loop operation for performing so probability states and 1 and 2 qubit primitives we are solving. 2 qubit C0 matrix representation here, control Q0 target 1 control bit and target bit C0. So with help of C0 representing 3 by 3 matrix representation, 2 qubit swap. Then Bell state generator, Hadamard gate and C0 gate combination. Finally, we are showing a 3 qubit Toffoli, that is a complementary controlled NOT Q0, Q1 and we are having all controlled 3 bits and target class. And finally, I am showing the states, 2 qubit initial states, 3 qubit initial states and apply gates like C0 example and swap example, Bell generator, Toffoli example. Finally, I am showing the probability labels and with help of bar chart I am demonstrating this figure. Okay, bar chart I am demonstrating for 3 qubit Toffoli. Okay, and this is the final output I am going to demonstrate here. Python space quantum. See here. So here I am generating, see I have taken comma separated variable multi-qubit gates. I am getting a C0 and C0 in and C0 out, swap in, swap out, Bell gate in, Bell gate out. So these are the operations. See here, and Toffoli gate CC naught on 110 3 by 3 matrix representation I am showing. So this is the way we are writing Python programming in order to solve complex applications very easily. The next last concept, uh, see Toffoli gate we have generated. The next one is a universal gates. So universal gates you might have seen in logic circuits, switching theory and logic, digital computer concept, universal gate, just like NAND gate. In classical computing, a small set of quantum gates can from all quantum circuits like Hadamard gate, Toffoli gate, C naught, controlled naught, or Hadamard gate, okay, and controlled not or universal. So these allow construction of arbitrary unitary operations need for quantum algorithm. So how we are going to demonstrate this application? Write a Python program to demonstrate the universality of quantum gate sets by comparing circuits built with the Hadamard gate, Pauli's gate, and C naught, and we have H and Hadamard gate, Toffoli, and C naught showing their produce equivalent output states with fidelity more or less equal to 1 or visualizing results. For this one, we are demonstrating Hadamard gate, C naught, and Hadamard gate and Toffoli C naught, and dependencies we are using like libraries or packages like NumPy for numerical computation, Matplotlib for visualization, Pandas for data set description. We are using, see, now this program I am going to demonstrate universal gates. CLS, clear the screen, notepad space. So write a Python program to perform universal gates by using Hadamard gate, Toffoli, C naught, and produces the output states fidelity 1 and visualizing the results. So we are declaring, we are importing NumPy, Matplotlib, Pandas. Then we are declaring a function with a loop function defining single qubit gates like a Hadamard gate and or Pauli gate or multi-phase gate we are using. Then define C naught gate like with the help of matrix representation, and input state we are taking, and we are performing circuits C naught and apply H gate, Hadamard gate, then controlled C naught, then circuit with help of C naught gate. Probabilities we are finding probabilities A, probabilities B. We are finding fidelity check, how strong and how inconsistent we are creating a data frame. States we are set A, set B, like combinations we are performing. We are taking CSV file, we are reading, then we are plotting bar chart. Okay, so we are taking width, height, the color is orange, sky blue, probability, and finally we are showing universal gates. So Python space. So this is the application demonstration of universal gate. See here, equivalent fidelity we are getting, set A, set B. We are getting universal gate operations with the help of orange, with help of sky blue. We are performing the two sets, set A and set B. Okay, so these are the universal gates demonstration. And you can see what are the examples of circuits using gate models. We have a famous algorithms like Grover's algorithm circuit. It uses Hadamard gate and Oracle multi-qubit phase gate, that is called Oracle, and a diffusion operator built from Hadamard gate and controlled NOT gates to amplify mocked states, that is called Grover's algorithm. How it works, I am going to demonstrate like Shor's algorithm circuit. So quantum circuit is a model and the basic building blocks like a gate model, sequence of gate models in the terms of qubits, and exponentiation sub-circuits, controlled gates, and the quantum Fourier transform we are using in Shor's algorithm using Hadamard and controlled phase gates. So teleportation circuit, it combines Bell state generation. You know, the combination of Hadamard gate and C0 gate is nothing but Bell state generation, and a measurement to teleport and unknown qubit state we are generating. So the first one is Grover's algorithm circuit diagram. So Grover's algorithm, it visually represents the sequence of quantum operations like Hadamard gate and combination Oracle, Grover diffusion, and measurements used in Grover search algorithm, especially in searching. Very fast we are getting the required element from the database, which finds the desired item in an unsorted database faster than classical methods. See, searching methods, you know, linear search, binary search, and these are the best searching algorithm is a binary, that is in classical computers, whereas in quantum computing we are having Grover's algorithm is very fast comparatively other algorithms like Shor's algorithm, etc. Why it is important? This Grover's algorithm reduces such complexity. Complexity is nothing but time takes for computation, order of n. So it is a mathematical notation. For order of n means n is equal to 5 elements. It takes 5 iterations. That is called order of n, classical search. Whereas in Grover's algorithm, order of square root of n. That means quantum search, very fast. So it demonstrates real world quantum speedup, and it serves as a foundation for optimization. Especially we are using this Grover's algorithm in artificial intelligence applications, big data applications, very complex applications, especially in cryptography and related applications. So where it is used, especially in database search. Okay, so we have numerous databases like freely available data bases like Kaggle database, GitHub database, UCI repository, banking sector, and other financial databases. Okay, so there we are using this Grover's algorithm. Then cryptography, especially unbreakable cryptography we can perform with the help of this Grover's algorithm. So brute force algorithm in classical computing, normal brute force algorithm, so weakening brute force attacks by speeding of key searches, this Grover's algorithm uses. Optimization problems, we are solving locating optimal solution among vast possibilities, especially in gaming applications, 8 queens problem, chess applications we are using. AI and machine learning, we are using enhancing search based traveling salesman problem, shortest path algorithms. In routing algorithms we are using. What are the examples of this Grover's algorithm? Especially in database search, password cracking in cryptography. See, very important password cracking algorithm, non-polynomial problems. Okay, solving satisfiability SAT problems faster, graph problems like depth first search, breadth first search, identifying specific structures or nodes in a large graphs. Like Facebook is a graph. How do I can find out Jain University in that Facebook graph? So in that complex database in Facebook, I am using this Grover's algorithm. Okay, and I'm finding a optimal solution for graph problems. So what are the steps in Grover's algorithm? We are initializing, starts with n qubits. It starts with operation 0, and superposition. We are using Hadamard transform. Apply H gates to all qubits, that is quantum bits, combination 0, 1 and both simultaneously to create a uniform superposition of all possible states. Then Oracle application, next the third step. The Oracle flips the phase, adds a minus sign of the marked target state so that it increases multiple operations. Grover diffusion amplification, inverts all amplitudes about their average, increasing the probability of the marked state and interaction, iteration, a repeat Oracle plus diffusion state about square root of n times. So see, we have seen such algorithms, linear search order of n time complexity, binary search order of log n, and whereas Grover's algorithm, the time complex is order of n times to amplify the marked state. That's why Grover's algorithm is very fast algorithm, especially in measurement. Measure the qubits with the combination 0, 1 and both simultaneously. The result collapses to the target state with a high probability. So this is the Grover's algorithm circuit diagram. We are taking n number of qubits with combination single qubit, multi-qubit, it converts into H gate. Then we are using Oracle gate and we are applying Grover's diffusion. Finally, we are getting Grover's iteration about the time complexity of square root of n times we are achieving Grover interaction. So that's why Grover's search algorithm is very fast because qubits undergo Hadamard transformation, Oracle marking and Grover's diffusion iteratively to amplify the probability of the target state. So now I am going to demonstrate this is the application. Write a Python program to demonstrate Grover's quantum search algorithm by simulating its steps. See, I am going to demonstrate Grover's algorithm. See here, I am clearing the screen, notepad space, then quantum. So this is the write a Python program to perform Grover's quantum search algorithm by simulating its steps and visualize how the probability of finding the target state increases with each iteration. So we are using Grover's algorithm with the help of probability of target state versus iteration, requirements like NumPy, Matplotlib. So I'm using gates, packages like NumPy for numerical Python, Matplotlib for visualization purpose. Utilities, I'm using Adamart gate. Okay, then I'm using a phase flip Oracle and diffusion function, Grover diffusion operator, and uniform superposition, and parameters. I'm using number of qubits. Okay, try 3 to 8, n is equal to 5, n is equal to square root 2 power n iterations it is performing. And then build operators like Hadamard gate, Oracle diffusion operations. Then optimal iteration count function we are developing. Algorithm like initialization, create superposition with Hadamard's, then track probability of target after each iteration and repeat Oracle plus diffusion, measurement simulate by argument maximum value we are getting, and we are finally demonstrating with the help of Grover's algorithm bar chart. Then I am showing how many n qubits, n states, target index, optimal iterations, final measured index, final target probability. Now I am going to demonstrate Grover's algorithm. Python space quantum. Okay, so this is the, see, Grover's algorithm, target state probability versus iteration, number of iterations after Hadamard's, and a probability of target state. Okay, so we are executing this Grover's algorithm step by step, and finally we are achieving the number of iterations versus probability of targets. Okay, so because of time, I'm moving to next concept. So everybody knows Pauli's X gate. We are representing in matrix. It is a single qubit. So Pauli's 2 up to you can call it as a pi by 8 toggle gate. You know toggle gate, phase, Hadamard, Pauli's. These are the single qubit gates. Then controlled NOT, C NOT, CX, control jet, swap. These are the 2 qubit gates. Then Toffoli gate, it's a combination of a complementary controlled NOT and a Toffoli gate we are representing in matrix representation performing logic gates in order to increase the high computing power within a fraction of seconds we are achieving the target. So flips a qubit state like NOT gate, that is turning into 0 to 1, 1 to 0. That is Pauli's X gate. Pauli's white gate, it combines bit flip and phase flip, introducing an imaginary factor. Then Pauli's Z gate flips the phase of 1 while leaving 0 unchanged. Hadamard gate creates superposition with a combination of 0, 1 and both simultaneously mapping basis states into equal probability amplitudes. Phase gate, that is S. So applies 90 degrees phase shift multiplying 1 by imaginary. Then pi by 8 gate applies toggle gate 45 angle phase shift multiplying probability 1 by e power I pi by 4. Then controlled not C naught gate. It flips the target qubit if the control qubit is 1. Controlled Z applies a Z gate to the target qubit when the control qubit is 1. Swap gate, it becomes 0 becomes 1, 1 becomes 0. Exchanges these states of two qubits. Toffoli gate, complementary controlled NOT gate, a 3 qubit gate that represents a 3 by 3 matrix representation that flips the target qubit only if both controlled qubits are 1. So last program, write a Python program to demonstrate minimal 2 qubit Grover search using a quantum gate model showing how an oracle and diffusion operator amplify the probability of the marked state and visualizing the result in bar chart. So for this bar chart, I am demonstrating, see here, last program for today's session, notepad space, quantum. See, write a Python program to perform and demonstrate 2 qubit Grover's searching algorithm using quantum gate models showing how an oracle and a diffusion operator amplify the probability of the marked state and the visualizing the result in bar chart. We are declaring import numpy matplotlib and try except we are importing the CSV file. Then we are printing quantum circuits implementing Shor's factoring algorithm. Shor's algorithm for factoring and Grover's algorithm for searching, and helpers we are using 1-bit gates, that is Hadamard gate, H on 2 qubits, oracle diffusion operator, and we are performing initial uniform superposition on Grover iteration. Probabilities we are finding, optional save CSV file, then C naught gate. Finally, we are showing Toffoli gate with combination C naught and Hadamard, etc. Now see here, Python space quantum. Okay, this is the final demonstrated application for today's. See here, Grover's algorithm, initial search and after Grover. See this orange color very fast comparatively. How many iterations? Okay, so it performs 2 qubit Grover circuit. We are solving very complex applications, search applications, especially in AI search algorithm like a traveling salesman problem and searching from a source to destination graph algorithms, etc. Okay, so these are the Shor's algorithm for factorization purpose we are using, whereas Grover's for searching algorithms. These are the applications of quantum circuits and gate models. I have explained already quantum cryptography for secure communication using protocols like quantum key distribution. Unbreakable cryptography we can perform with help of quantum circuits and gate models are the basic building blocks for quantum computing. Quantum simulation we are performing modeling molecules, chemical reactions and quantum systems, drug discovery, material science we are using quantum circuits and gate models. Optimization problems like non-polynomial hard problems like logistics, finance and resource allocation we are using quantum circuits and gate models. Quantum machine learning algorithm like enhancing data classification, clustering, association rule mining, outlier detection, pattern recognition with the help of quantum algorithms like Grover's, Shor's, and etc. In such algorithms, speeding of unstructured data like audio, video, text, graphics, animation applications, we are using this Grover's algorithm. Shor's algorithm breaking large integer factorization so that we are making plain text to ciphertext with unbreakable cryptography. We are using Shor's algorithm in RSA cryptography. Quantum error correction, we are implementing fault tolerant quantum computation. This quantum computing circuits and gate models we are using. Financial modeling, especially in risk analysis, option pricing, and portfolio optimization we are using. In artificial intelligence, these quantum circuits and gate models boosting AI systems with the quantum enhanced models like machine and deep learning, AI models and statistical models. Big data processing in order to handling high dimensional. See, if the dimensions mean the columns, if you are increasing number of columns means automatically the complexity is increasing. So that's why efficiently, if you want to solve, not like classical systems by using this circuit, quantum circuits and logic gate models, we are solving these problems very easily. So with this one, I am closing. And these are my so many 175 so far. I have conducted international workshops. This is the latest one. These are the upcoming one. So this is latest one. I am going to demonstrate a 3-hour session. This is you are getting certificate from my university, and this is the link. If you want, you can search in Facebook, LinkedIn, Instagram with my name, Dr. Asadi. You will find the link and you can register for this workshop. And my dear participants, any doubts, if you are having, please ask me now. This is now time is yours. You can ask me. This is my contact details. If you want to collaborate, collaboration research, research articles, conference papers, thesis, or any book chapters, books. Uh, Thanks to Sunita Madam, recently she requested for book chapter combination. I have accepted her invitation. Now I'm submitting and my acceptance for her for publishing book chapter and all. And thanks to management of Chain University, thanks to ma'am giving this opportunity, principal, vice chancellor, and my dear colleagues, my dear participants. If you are having any doubts, please ask me right now. Madam, how many participants are there, madam?
172, sir.
Oh, thank you, sir. Any feedback from participants?
Dear participants, the forum is open. You can feel free to raise the questions.
Yeah, please. So please subscribe my channel, Dr. Asadi Srinivasulu. So far only 5 members subscribed. I'm expecting 170 members. This is my third event program at Jain University. Thanks to previous coordinators, Vikram and Sunita Madam, and a few more my friends are working in Jain University.
Dear
Thank you, sir.
participants,
Any
please.
any queries? Any queries from the participants?
Hello, good evening, sir.
Good evening, ma'am. Please introduce yourself and ask a doubt.
Yeah, myself Harshlata Petkar from Maharashtra, Mahatma Gandhi International Hindi University.
Yes, ma'am.
Basically, I'm very much eager to know about
Quantum computing.
Quantum computing. But can we relate quantum computing with humanities? Because all the topics that you have covered are all technical.
Yes.
cryptography, then machine learning and
Yeah.
artificial
Sorry. I
intelligence.
don't know. I thought that all computers background. That's
No.
why.
Yeah, I'm having computer background, but
Yeah.
still I want to know that can we connect quantum computing with the humanities fields or background people, or can they be able to do the quantum computing for their field?
Yeah, wonderful question, ma'am. It is a quantum computing. Indeed, it is a multidisciplinary subject. Okay, you can apply whatever the irrespective of the domain. Not only humanities, not only civil, not only environment, not only electronics, not only computers. Wherever complexity is there, we are performing quantum computing circuits and gate models, these quantum computing algorithms. We are using especially in big data applications such as weather forecasting, traffic data analysis, and human being related any kind of data, not only environmental, not only medical, not only engineering, any irrespective of the domain. The quantum computing came from the quantum mechanics in terms of qubits, quantum bits with the combination superposition and entanglement for speed of the process and the computation purpose. It shows the parallel computing in order to get fast requirement, fast achievement of application. Okay, Ranga, raised your hand. What is your doubt,
Thank
please?
you, sir.
Yeah, ma'am. Hello,
Hello.
Ranga.
Hello.
Yeah.
Hi, good evening, sir.
Good evening, Ranga. Please introduce yourself. Where are you from?
I'm Dr. B. Rangaswamy, as a professor in Engineering College, Hyderabad,
Oh, which university?
JNTU.
Oh, JNTU, sir. Yeah, nice to meet you, sir. Please.
I have a doubt about the entanglement. Can you explain
Yeah,
about the
entanglement.
entanglement?
Yeah.
Or the physical
What is
meaning
your
of
doubt
that entanglement?
exact? Yeah. Entanglement is nothing but, see, two or more particles making a link, association, wherever it is. See, 0, 1, and both simultaneously connecting 1 to 0 to 1, 1 to 0, many combinations. That link is called entanglement, so that we can generate numerous operations with help of entanglement. Sir, like many operations we can perform parallelly, simultaneously. We're not like a classical computing, like our computer servers performing on the basis of 0 or 1 combination binary systems. Whereas in quantum computing, it uses qubits with combination 0, 1, both simultaneously it becomes superposition, and one or more particles becoming connect and linked, okay, and perform various operations like in entanglement, so that we can perform complex operations very fast and very easy.
Thank you, sir.
Yeah, very good. Thank you, sir. Nice question. Is there any other feedback from the participants? Any feedback, whether it is negative or whether it is positive, please give feedback. Our next session will start, I think. Sir, coordinator, sir.
Yes, sir. Yes, sir. We are
Yeah,
here.
please. Maybe sir is waiting or.
Participants, any more questions from your side? Okay. I think there are no more questions. Thank you so much,
Thanks
sir.
to Jaidi madam, sir. Jaidi madam, sir. Big thank to Jaidi madam. Yeah.
Okay, sir. Thank you, sir. Thanks, Dr. Asadi, sir, for your wonderful and informative session. The second day of the FDP featured a detailed session on quantum circuits and gate models with applications of quantum computing and explained quantum classical computing integration framework. He introduced the basics of quantum gates, including single qubit and multi-qubit operations with the practical implementation and workflow of quantum circuit and gate models. The importance of unitary transformations and their role in ensuring reversibility was highlighted. Once again, sir, thank you so much for your wonderful contribution.
Thank you, sir, for giving me this opportunity. Next upcoming workshops are there. This is yours, and next one more workshop is there. If anybody interested, you can contact me through WhatsApp and anything. I'm going to quit, sir.
Yes, sir. Yes, sir. Okay, now it's time to invite the other resource person of the day. It's our privilege to welcome Dr. Gururaj H.L. Sir, Associate Professor in the Department of Information Technology, Manipal Institute of Technology, Bengaluru. He holds a PhD degree in Computer Science and Engineering from Visvesvaraya Technological University. He has 14 years of teaching and research experience at both UG and PG level. He is a senior member of ASIM and IEEE and lifetime member of Cryptology Society of India. Dr. Gururaj appointed as ASIM Distinguished Speaker from 2018 to 2021 by ASIM US in Council and is one among 15 speakers across India. He is honored with ASIM India Eminent Speaker for a tenure of 2024 and 2026. He received Young Scientist International Travel Grant from SERB, Department of Science and Technology, Government of India in December 2016. He also received Best Project Guide awards consecutively for 4 years at Malnad College of Engineering, India during 2014 to 2017. He also received award for outstanding research publications by VGST, Government of Karnataka in 2023. He worked as special issue editor of Springer, Elsevier, MDPI, IET, and Frontier journals. He has published 23 authored and edited books at Springer, Elsevier, Taylor and Francis, IGA Global, and IIT publishers. He is an editorial board member of various international journals. He has published more than 200 research papers in peer-reviewed international journals and book chapters. He has presented more than 75 papers at various international conferences and received Best Paper awards. He has granted with 1 Australian patent, 2 Indian design patent, and 6 Indian copyrights. He has delivered more than 500 technical talks across the globe, to name a few. ASIM Distinguished Talk at IIT Kanpur in 2019, Plenary Talk at NIT Surat in 2020, Keynote Speaker at Update Europe Conference in 2020, and Keynote Address at 8 International Conference ICMLT at Norway in May 2024. He is honored as Session Chair, Keynote Speaker, TPC member, Advisory Committee member at national and international seminars, workshops, conferences across the globe. He received grants from various bodies like SERB, DST, CSIR, and AICT, Government of India, to organize international conferences and seminars. Currently, he is guiding 6 PhD scholars. His research interests include AI, blockchain technology, cyber security, wireless sensor network, ad hoc networks, IoT, data mining, cloud computing, and machine learning. I request Dr. Gururaj sir to deliver the session on quantum algorithms and computational complexity. Over to you, sir. Thank you.
Yeah, thank you so much, Dr. Ramkumar, for giving the introduction and for inviting me for this FDP. Thank you so much, Dr. Ramkumar. First and foremost, I am apologizing for I'll not switch on the camera because I'm traveling. Actually, my session was at 6 and it was swapped because of the other professor busy schedule. So as I'm traveling, I could not able to switch on the camera. As I requested, I take up this session. Yeah. Let me share my screen. It's once visible, please respond or acknowledge.
Sir, you please share.
I think screen, is my screen visible?
Yes.
Yes, sir. Yes.
I hope the screen visible.
Yes, sir. Screen visible.
Yeah. Thank you. First and foremost, that across globe, when I got an introduction towards quantum and why quantum plays a very important role. I think you probably heard of this from basic start of computers. We all tend towards having the data of each or for that matter. I think we all know that it's in the form of one. Why? Because our this data. It might be a form of data. It might be text data, audio data, video data, multi-data, or any data for that matter. All the data is connected to binary data. It's something that to if it is something like an image, we have to divide that into a pixel form, and end of the day, we have to convert that to 0 or 1, either grayscale or RGB format. And if it is a video, we'll convert the video to scenes, scenes to frames, frames to pixel, again pixels to 0 and 1. End of the day, whatever the data we have to convert the data in the form of. Let me do of this. Why are doing this? We have to understand, right? In the context of defining why we require this quantum is one such thing which light 0 and 1. Okay. Yeah, I'm even started learning all this. Guys, if you have any questions at any point of time, please ask me a question. So I'll try to answer that. I'm not well versed with this because my core area is not algorithms. I'll try to give my overview or my perspective. First of all, if you heard of this name, what is quantum refers to using the principles and features of mechanics, the fundamentals, which involves basic if you want to get the best up the quantum of the smallest of line, it can small unit. And then we have a combination of machine learning and this quantum, which we call actually quantum is something where we are dealing with uncertainty principles kind of thing, when which usually people will have that both 0 and 1 cannot be on the same state, right? Okay, but now we can have both the states. That was all about quantum. Okay. Which mainly results to very smallest unit of energy, or it might be matter. In basically, if you want to call it as which we derived from that quantum physics or quantum mechanics, in which we'll call it the process of having the smallest unit called as quantization. Okay, and we'll call them as discrete packets of that stream of light which are embedding or which are projecting from that source. Okay, so that is all about quantum. And what about the machine learning? Machine learning, which we use existing data set, or it's going to use existing or a collection of data, and it's going to process using some basic mathematical models, and it's going to get it on as okay. So it's going to use basic mathematical models to improve the performance. This is all about what we're learning right now, it's called as quantum, learning. Quantum machine learning is nothing but quantum computing plus quantum computing, which combines, as I said, it cannot be have either 0 or 1. It can have other state that's called as qubit state. Okay, that's all about quantum. And machine learning, we are going to use, all basic mathematics to do certain operations like classification, clustering, and all using fundamental foundation math. And we have quantum algorithms. Okay, so quantum algorithms, which uses explicitly to do some operation on quantum machine learning, we'll call them as quantum algorithm, which leverages quantum phenomena. Like basically, quantum phenomena happens with the help of three phases. One is superposition and entanglement and quantum coherence. Okay? We'll see one by one. Quantum superposition means that particles that can exist in multiple states simultaneously. As I rightly mentioned, if you go for any machine learning algorithms, we can have either 0 or 1. Like, and if we would have taken example of decision tree, either we are end up with either 0 or 1. But this is something, a state in which that lies between 0 and 1. Okay, it might be 0.1, 0.2 until how will these? It cannot be discrete like 0.1 and 0.2. It can be 0.1111 or 0.1112. It goes on. Okay, so we can have any number of states that between 0 and 1, we can call it as superposition. Okay? Which can have n number, more number of states. Okay, so what is entanglement, which correlates between qubits, the state which have exactly 0 and 1, that works for the. I think if you observe the machine learning algorithms, neither other basic machines and bits or one we have, correct? There other state, no, that state represented. So the third the quantum basic
मम्मी फोन कैसा
if you have any questions, you can put up your question. Any questions? I heard something from the audience. If no,
Don't ask why you do.
is my voice audible? Sorry.
Sir,
Yes, sir. Yes, sir.
You are
Audible. Now you are audible. sir.
Now it's audible.
Is my screen visible? Hello?
Hello.
Is my screen visible, right?
The screen is not visible, sir.
Is okay. One second. Hey,
Why-
I'm
why
very
is also-
apologized for this
why-
because
why-
I'm traveling.
why is also
Second one.
breaking, sir?
Give me a second. One second. I've shared the screen actually. Okay. Okay.
Yes, sir. Your screen is visible now.
So if something happens, I'm really sorry for that because I'm traveling right now. As I was depicting, mainly we require three things in which leverages quantum phenomena. One is superposition, and one is entanglement, and one is quantum coherence. Superposition means that, as I clearly mentioned, we have either the zero state or the one state in case of your basic machine learning algorithms, or like something like decision trees and all will end up with either 0 or 1. But in case of this, we'll have other states also, like it might be 0.1, 0.111, or whatever. So that states, we can have multiple states, hence it's called a superposition. And entanglement means that it's going to perform various multiple operations with those states, and with the help of qubits, will represent them with the help of qubits, as in case of other algorithms, will represent with the help of bits, will represent here with the help of qubits. Okay, and quantum coherence, using complex states, it's going to maintain those superposition. That's also important. Okay, we'll understand why this some quantum computers usually used to solve machine learning. Something like quantum machine solve algebraic problems. It's involved machine learning and some and it's going to involve quantum component analysis. It's going to solve as usual, it will start with as usually it start with giving the inputs and machine learning in the same way, but later on it will use quantum mechanism to adapt that. It can be of quantum perturbation and kernel methods, or it might be quantum optimization. Yeah, and basically the quantum bits or qubits can be represented with the help of this form of notation, which I've shown. Commonly, it is represented by angular brackets, called usually we have to call it as angular brackets. Okay, angular brackets will be used to represent quantum, and we'll call it as BRAC and one part, and KT the other notation. Okay, so and it's also called as Dirac notation that will be used to write the equations. Okay, the notion will be uses angular brackets and a vertical bar in between to construct bras and kits. The first part is called as brackets. We determine bra, and the other part we can call it as kits. Okay. Yeah, I think you can able to see here, right? The first part will be started with the angular bracket. That is the first notion. That is the first part. And there's a differentiator we have. The other part we can call this kit that can be represented like this. Okay. Mathematically, it denotes the vector in a complex vector space V. That's called as quantum system. That is all about the kit. And Brahmins, it looks like a linear function that maps the vector to the number in the complex plane. That is all about the thing. And end of the day, they all belong to the complex plane. Yeah, as I clearly mentioned, quantum computer uses qubits instead of bits, which are used by classical computers. The bits are commonly used. A bit refers to binary digit, and it forms a basic classical computing. The term qubits stand from quantum binary digit, while bits have only two states, as I already mentioned, either 0 or 1. Qubits can have multiple states at the same time. The value ranges between that 0 and until 1. Okay, this is a pretty simple example to determine, right? I have a coin and I'll toss the coin. Okay, so once I toss the coin, this another thing for people. What I'll do is I'll toss the coin as I want. When I to better understand, if you want to toss a coin, we have either heads or tail. If you represent head as 1 and tail as 0, while the coin is being tossed, we don't know which side it has until we stop it or it falls on the ground, right? So looks at the coin toss shown below, or you can observe here the animation. We can either predict one. We can have a transition, right? When you flip, then we can have a transition. When you flip, it is started as 0, and during the before end up with the end stage that either head or tail is the end state. We have various transitions when you're flipping. No, that state is all about superposition states. Okay, so. This is one simple example for understanding how it works. That is one. Okay. It is likely the various states which are said either high, while on a flipping, it was have various likelihood to check whether it's 0 or 1. That flipping, which we results, it's called as superposition collapses. Okay. So this is the one that is called as no complex plane we can have, and can see here. Similarly, what I said, we can have. So where you can so that okay, they have taken the example of a cat. In this example, they have given the example of a cat. Let us consider that is sleepy or is, for example, a cat is sleepy. Okay, what will happen in mind? A cat is alive, is dead, right? This is one more famous scientist. He's given the example. It's called a Scrodlinger cat. This idea is if the cat is sleeping means we have to determine the cat dead or it is alive. So that state, okay, the alive and dead state, the range between those two states is commonly as entanglement, or we can also spell state. So on the other side of the slide, you can see they clearly the type of omega can see on the other side. That is called as the state between 0 and what's called as bells. Okay. This is called how we sort of the know how to represent the things. You can see here. That is 0 is alive or 1 is dead. You can see here. That state represented with the help of we can have 0, 1, 0, the state. That's all about the cat. How it. Perform any machine learning algorithms or if you want to find them to GPUs or GPUs and all. For quantum machine learning algorithms or quantum algorithm machine learning algorithms, we will not find normal CPUs be designed to operation. To the case of partition, just going to have Okay, this is all about the same example which I've depicted. In this example, we have a cat example that taken, which I mentioned that either cat is alive or dead. You can see over in the picture. In this example, what we're taken is we have either 0, 0, or you can see here, if a cat is sleeping, what we can have an assumption is either the cat is alive or the cat is dead. So that assumption we can do with the help of the states which lies between 0 to 1. Okay, you can see here, right? So the same notation I have represented on the other side, 0, 0 and 1, 1. Okay. As I rightly mentioned, I already mentioned that if you want to use any machine learning algorithms, we are commonly going to use, CPUs, GPUs, or TPUs and all. But as we all know that if you want to perform, in case of GPUs and all, if you have machine learning algorithms, either we have 0 state or 1 state, right? So it's not require much, it does not involve complex operations. But in case of quantum and machine learning algorithms, and it's going to involve superposition states like 0, 2, 0 0.1, 0.1111 and all, until 1 state, we have n number of complex operations. We have to perform those complex operations with the help of, obviously with the help of quantum computers. Okay, they will use special purpose AI accelerators which enables the states to perform and operate in an efficient way to get the answers in a accuracy in a better way. This is just a comparison with classical programming, how it works, classical machine learning, and classical quantum machine learning. For example, if you would have taken a task, classical programming, it's something like to check whether a given number is even or odd, which uses an approach called rule-based approach, or we can call it as deterministic approach, either even or odd. And computation unit for this is, it will be either 0 or 1. We all know that it will work with the help of bitwise. And the type of input data will be user explicit values we'll have to use, and we have to check whether it's an even or odd user input. And learning capability, we don't have any fixed learning capability. We can have, we don't have any fixed, we can have any logic for that matter. And the speed or the scalability, if it is as it is very simple task, it will be very faster, limited for high complexity. Okay, example of framework like we can implement any Java, Python, whatever. Okay, so this is something like we can able to perform the operation. If we have checked the operation of something around classical machine learning algorithm. Something example, we can have a prediction if a customer will churn or rate. It's to calculate the churn rate. And approach, we can use learn patterns from labeled or unlabeled data set, something like that. And computation unit will be, it might be of we can have it can use some bits plus some mathematical models. As I already mentioned, we can have regression or trees, and a large input of data set will require. And learning capability will be, it will learn from the data, which improves the performance. Okay, by experience, as the data size keep on increasing, we are going to improve the performance of that. Okay, and how about the scalability and speed of that? It will be good with GPUs, but still limited by classical hardware. And the example framework like scikit-learn, TensorFlow, PyTorch, and all we have. And the use cases, we can have either image classification for, it might be for a plant disease or whatever, all those predictions and all, sentiment analysis or whatever. Okay. When come to the quantum machine learning algorithm, quantum machine learning, something example like optimize drug molecule structure using quantum state. Okay, obviously molecule structure we cannot determine just with the help of 0 and 1. So we can have obviously with the help of quantum states, which will learn from data using quantum algorithm and qubit-based representative. And qubits can be superposition of 0 and 1 simultaneously. And it can going to use input data of quantum encoded data. Even though you pass audio data, video data, whatever the data for this quantum algorithms also, end of the day, it will convert the amplitudes of quantum states. And learning capability, yes, learns via quantum enhanced processor, and it obviously potentially faster. And potential exponential speed up for specific problems. And example framework, we have Qiskate, Penny-Lane, TensorFlow, and Quantum. In use cases, you can observe quantum chemistry optimization and high-dimensional clustering. These are some examples where in India also people are working on quantum chemistry and or the molecule structure and all on this. Just a transition, how happens or how occurs from a classical software or machine learning engineer to quantum machine learning engineer. And obviously, we require machine learning to quantum machine learning. Classical system struggles with high dimensional data and complex computation. Quantum system offers exponential speedups for such ML tracks. Okay, just the overview. Obviously, if you want to be just a quantum machine learning, just you have if you have a mathematical foundation with machine learning will not suffice to be a quantum machine learning algorithm or a quantum machine learning engineer. They require foundation of physics, computer science, mathematics, or AI. That's fine, educational foundation. When it comes to technical skills, you require Qubit, TensorFlow Quantum, Python, linear algebra, and optimization. When it comes to business domain understanding, you should understand how the supply chain works from the start to the deployment until the production and everything, and finance if he has to know. And soft skills, interdisciplinary thinking, problem mapping, adaptability, and curiosity. And just an overview of how the quantum machine learning we have what are benefit or what are application or what are use cases we can have for this. If you would have taken the optimization, no, the major application you can think of this, it might be supply chain scheduling, route optimization we can do. And it does not mean that what I'm the application what I'm showing it can be happened only with the help of quantum machine learning algorithms. No, it does not mean that. It will which can be done with the help of basic classical machine learning or deep learning algorithms. But if you have used quantum machine learning algorithms, we'll get more accuracy and more optimized solutions we'll get. Okay. What's the quantum benefit for the first optimization category? Faster coverage in complex problem spaces. If you would have taken more time in case of existing, it will have quantum, faster optimization will get. And if you would have taken classification category, image or space recognition using support vector machine or whatever, so it will use scalability with large data set. Okay, scalability can be improved, can be added up with huge and enormous number of data, and you can get a better output. Okay, clustering, if you have taken the category, customer sentiment segmentation, or it might be anomaly detection using quantum K-means algorithm. And obviously, if you would have used this quantum K-means for customer segmentation or anomaly detection, it will provide efficiency in high dimensional space. And the next category is dimensionality reduction. Obviously, dimensionality reduction can be done with the help of PCF, principal component analysis for feature selection and data visualization. If you have used quantum PCA, obviously we have improved pre-processing speed and insight of that dimensionality reduction we can able to achieve. And if you have taken generative models, quantum VAs or GANs for data augmentation, realistic sample generation in data scale domains, and if you have taken pattern discovery, quantum Boltzmann machines for recommendation systems or NLP can be used. And if you have taken the quantum benefit, capturing deeper probabilistic correlations we can have. If we have taken neural network training, we can have speed up back propagation using quantum inference. And if we have taken a benefits of application, fewer iterations to optimize weights. As we all know that it's pretty fascinating for quantum chemistry, for drug discovery or material science, it will be used. And if you want to have a benefit, solving complex molecular simulations. Okay, and anomaly detection or outlier detection can be done in network traffic analysis or fraud detection in finance. Again, the benefit will be stable pattern detection in noisy data also. Not only noiseless data, in noisy data also we can able to detect the fraud and also can able to analyze the traffic. And if you have taken a reinforcement learning, training anonymous agents like self-driving cars and UAVs, unmanned aerial vehicles, for quantum benefit, we can have faster policy optimization via quantum enhanced strategies we can have. This is just an overview of the applications, how we can, why we have to shift towards quantum, basic machine learning to, why we are shifting to this one, okay? Quantum machine learning algorithms. Yeah, this is directly how the by taking the supply chain management, how this quantum machine learning and classical machine learning will work with the case study of supply chain. I think probably you might have been having supply chain from from the raw material to the product delivery to the customer. The complete operation will have various stages. We don't have any intervention of the middleman person, and that operation without any middleman person we can call it supply chain management. And how we learning and how we can does with the help of quantum machine learning. We can see over here. The main goal is to predict future customer demand to optimize inventory and reduce the cost. That is all about the goal. Same goal, but with improved speed and accuracy for complex data in case of quantum machine learning. And how it works in classical machine learning, which uses algorithms like regression, decision trees, neural networks on historical sales data and trends. But in case of quantum machine learning, uses quantum algorithms leveraging parallelly operating and entanglement to analyze complex and high dimensional data. An example, retail company predicts next month's product demand based on past sales and seasonality and promotion. Based on this, but in case of quantum machine learning, retail companies analyzes complex interaction between sales, supplier timings, weather, and social media trends simultaneously. All these operations, it might become sales, supplier timings, weather forecasting, social media trends. All things will be determined simultaneously with the help of supply chain. Some advantages we would have used machine learning. Widely used, obviously, we all know that. Pretty fascinating across the globe and effective for moderate complexity and dataset sizes. But in case of if we would have used QML, we have faster processing of large complex datasets for better at capturing subtle correlations and uncertainty. Some limitations may require high computation for very large or complex data, limited patterns, recognizing interconnected variables, which are not. Obviously, we have dependent variables, right? So obviously, we have that. But in case of quantum technology, because it's not well versed, I think if you have heard of this in any quantum labs across India, we have hardly 2 or 3. Very rarely we found quantum labs, so requires a quantum hardware, currently limited availability, but promising in the future impact. Obviously, as we have, it's going to provide better accuracy. I think it will be a future impact. Okay. And potential impact on supply chain helps in inventory management, demand forecasting, and route optimization. But in case of QML, enables enhanced forecasting accuracy, optimize supply routes, and better resource allocation to factor in deeper data analysis. This is just an application of supply chain management, how it works. I should have taken quantum machine learning algorithm. How the algorithm based on the data we can have the representation here. This represents here the y type of data, and the x-axis represents quantum machine learning type of algorithm, which whether machine learning algorithm or classical algorithm we have to use. I can see here on the first quadrant we have CC that indicates classical type of data and classical machine learning algorithm. And we can have, if you would have a data of classical, and you can apply quantum algorithm. And if you would have used quantum data, and you can apply classical algorithm. And at the last stage, you can use quantum data, and we can use quantum machine learning algorithm. Okay. See, classical ML, example deep learning or whatever, and CQ, if you would have used classical data with quantum algorithm, machine learning on classical data using a quantum computer algorithm. And QC means classical machine learning on quantum data, and QQ means quantum data and quantum machine learning. We can have all these operations to check or to do the various operations like ablation. We can will have. This is just an overview of how a quantum circuit and neural circuit will be. We can obviously, in case of neural networks, we can have input layer, hidden layers, and output layer. So quantum circuits is we can if you I think probably you might have been heard of this name quantum neural network, neural circuits or neural networks. Quantum circuits are something like sequence of quantum gates and operations applied to qubits, which performs a particular task. Okay, some examples or some how the basic steps that are required for required for quantum circuits are basically the first component we require is qubits, the basic unit of quantum information. We all know that. and we require quantum gates, okay, which operates the or manipulates the qubits, such as it might be rotations, or it might be measurements, or it might be entanglement, can be done with the help of quantum gates, the second important component. And the third important component is control flow. Classical control structures which determines the sequence of operations, it's called as control flow. These are basic three components of quantum circuits. If you would have taken the types of quantum circuits, we can have variational quantum circuits, quantum error correction circuits, we can have quantum simulation circuits, and so on. We have a number of circuits. Any circuit for that matter, we're going to have these steps. Okay, it might be of variational quantum circuits, or quantum error correlation correction circuits, or quantum simulation circuits. The main three components are qubits, quantum gates, control flow, and any circuit for that matter, we have to follow these steps. Okay. The first step is called as data encoding. First, we have to convert any classical data or any data into quantum states. Okay, that is they are representing here, and something like if you have taken R, it stands for rotation. That state, the bifurcation. This is the representation how to do the data encoding. The first step is any data, we have to represent that with the quantum. And the second steps involved parameterized quantum circuit. How how circuits with adjustable parameters like we are as we do in the case of neural networks, right? Using some various functions like min, max, or whatever. So here also it will allocate some parameters for all the neural network operations. Okay. And at last, we should have measurement and cost function. Complete after adding the parameters with the help of weights, we have to run the circuit and measure the output. Then we have to calculate the cost function. So in that cost function, we can use any gates for that matter to measure. It might be something called hard math gate or X gate or single gate. They all comes under qubits gate or the superposition gates. You can use those gates and you can calculate the cost function. And you have to optimize the parameters with the help of training. We choose classical optimization algorithms like gradient descent, Adam optimizer to change theta, so that cost becomes smaller. That's the next step. And this is just an example to explain or to overview how the quantum algorithms or quantum circuit will work. Build simulations inside existing leverage existing optimization tools. Will help us to boost the scalability of this. Okay. No hardware based. We can have stable tablets, don't want any simulation. Just because we have real-time access to information, measurements, and need to do that. Okay. We have various quantum machine learning algorithms to implement this simulation, either hardware based. These are some algorithms which I'm depicting just quantum machine algorithms, like we can have linear algebra simulation, or such algorithms like quantum K-means algorithm, quantum enhanced reinforcement algorithm, quantum annealing, quantum neural networks, hidden quantum Markov model, pattern matching and classification, sampling techniques. They all are the part of various quantum machine learning algorithms. Just a simple notion how this quantum machine learning algorithm for pattern and pattern matching and classification. Okay, so you can see here in the PPT which I'm showing here, which explains the pattern matching using quantum machine learning algorithms and how it's going to classify the characters which are depicted in this. Okay, there's a targeted image in this, a set of references which are in the array. Okay, so how it does is it's going to use it might be of any pattern matching algorithms. Use classical to first encode the data, classical to quantum encoding, then quantum circuit for calculating the distance between them, classical post processing, and the reference image with the minimum distance. Which minimum distance going to have that's called the final output of this. Some benefits, if you have used algorithms which uses for fast matrix operations. Some applications we can use PCA regression kernel methods. For such algorithms, we can use QMLs like quantum K-nearest algorithms. Faster neighbor search, we can do that using applications or something like classification or recommendation. We can do that. Quantum reinforcement learning, better exploration and policy optimization. And robotics, AI, agent finance. Quantum annealing solves hard optimization problems, which helps feature selection or training the models. We can do that. Quantum neural networks leverage quantum circuits in learning for classification and function approximation. Hidden quantum model sequential data with more can be used for speech recognition, text classification, bioinformatics. Pattern matching classification, quantum similarity for classification task that will be used for image and text recognition. For the usages, sample complex distribution, and applications generate models and information. Libraries which are Pennyling is one library can use it or can it was developed by Zandu for hybrid kernel. We can have Qubit machine learning, IBM's toolkit for QML, TensorFlow Quantum, TFQ. Before it was TF TensorFlow, we have TFQ, which was developed by Google, and Circ, which again Google framework for NISC circuits. QML, Quantum Machine Learning Toolkit by D-Wave. We have these are the tools, various tools which are available for the quantum machine learning algorithms. Okay, some simulators for the understanding. If you can't able to implement, perform that on the real-time hardware, we can go with Qubit Air, pen and lighting. These are some of the simulators which are embedded. These are the platforms where we can have the access, like IBM Quantum, Amazon Bracket, Azure Quantum, Zandu Cloud, Gate QCS. These are the platforms I can use. Okay. And I'll finish off my just an overview how the quantum machine learning algorithms can be used. Quantum machine learning algorithms combines the power of quantum computing with classical machine learning techniques.
ಸುಸು ಮಾಡ್ಕೊಬಿಟ್ಟಿದ್ಯಾ ಹಿಂಗ್ ನಾನು ಪ್ರಿಂಟ್ ಔಟ್ ತಕೊಳ್ತೀನಿ ಅಂತಾನೆ
to potentially solve complex problems faster and more efficiently. By leveraging quantum algorithms, it aims to enhance data processing. It also aims to enhance optimization, pattern recognition, task behind classical limits, paving the way to breakthrough in AI and other fields. While still in early stages, ongoing research and development in quantum hardware and software, which promises existing advancements. Okay. I'm giving the glimpse of the quantum circuits and quantum machine learning algorithms. It's not about the depth knowledge of that. See, with the help of quantum circuits, obviously we can speed up the first point, the takeaway, and we can have an improved efficiency, and we can have handling high dimensional data. And we can have various quantum machine learning algorithms like quantum machine, support vector machine, commonly called QSVM, quantum k-nearest neighbors, commonly called as QKNN, or quantum neural networks, QNN. This is the algorithms we can use. Which will be happen for various complex stages of superposition. That is all about the presentation of my session. That's all from my side. If you have any questions or something, you can put up your question. And before that, I thank the coordinator to out, or if you want to website, area of my. If you really wanted to collaborate, or if you want to work on these domains, kindly feel free to contact me. Just type my name in Google, or just can have it's me Guru.in. You can get the data. Okay, that's all from my side. Thank you so much for your patience listening. If you have any doubts or any questions, it's open for you people.
Participants, feel free to raise the questions.
If you don't have any questions, please, if you wanted to collaborate with me, this is the website. And I mainly work on, as I rightly mentioned, cybersecurity and blockchain is a core domain of my area. Feel free to contact me. I have all my works, everything, all details are here. You can contact me via all these platforms. Thank you. Shall I wind off? Dr. Ramkumar.
Yeah, yes, sir. Okay. Thank you so much, sir, for your wonderful and informative session. The day 2 FDP session on quantum algorithms and computational complexity provided the participants with deepest insights into the algorithmic foundations of quantum computing. The session began with an introduction to the efficiency of quantum algorithms compared to the classical ones. The session also highlighted the challenges of designing efficient quantum algorithms, applications of quantum algorithms in optimization, cryptography, and data processing were outlined. The importance of scalability and error handling in real-world implementation was addressed very well. Overall, the entire session gave the participants a structured understanding of how complexity theory underpins quantum computation. Thanks to all my dear participants. We are closing today's fourth session of day 2. We will see you tomorrow for day 3 sessions on quantum error corrections and quantum computing in industry, applications, and case studies.
Excuse me, sir. This day 2 session 2 feedback is, I
Yeah,
think it is
yeah, yeah.
wrong. It is asking us to do. It's already filled. It's saying that message.
No. Yes, ma'am. Yes, ma'am. Our team is working on that. We will post the
Okay.
link quickly. Thank you for your comment.
Where? Should we wait here?
Yeah. We will post now.
Okay.
Okay. Participants, thank you once again. We are winding up the session now. Thank you. So I request the participants, please fill the feedback once if it is shared. Thank you.
తినేలా మీ నాన్న ఎట్లా ఏది తినడు నాటి కాపర్లా కూర్చుంటాడు
Yes, you are given, madam. Day 2. Again, Srinivasulu. So, dear participants, both the links are there. Session 1 and session 2 links are there. So sorry for some glitches because the reshuffling of the speakers. So now session 1 and session 2, both the links are given, feedback links are given there in the WhatsApp group. You take your time, and the forms are active till 9:30. So you take your time and fill the forms. Thank you.